In this video we will revisit MMSE processing, which is the optimal receiver processing, and we will look at its asymptotic behaviors and see that when we have high SNR or when we have many antennas, then the optimal processing turns into a special form known as zero forcing processing. We will look at the particular properties that zero forcing has, and we will see that we can compute a closed form capacity lower bound when we are assuming that zero forcing is used, and that can be applied at any SNR for any number of antennas. And then we will compare MMSE processing, zero forcing, and maximum ratio processing. We begin by recalling the system model for the uplink of a massive multi-user MIMO system. We have K users, and they are transmitting different signals, Q1 to QK. Each of them are multiplied with the maximum power, rho uplink, which is square root on. And then there is a power control coefficient for every user, eta 1 to eta k. They are in this diagonal matrix, and we take a square root of them as well. The signals are traveling over the channel characterized by the channel matrix G. Every column is the channel vector from one of the K users, and the base station receives a signal Y, which is m-dimensional. This channel matrix is m by k, and we have a vector with the receiver noise, also m dimensions. And when we are interested in decoding the signals from different users, we will consider using linear processing, which means that for every user I, we select a receiver filter, AI, which is a vector, also m dimensions. We compute the inner product between Y and this receiver filter, and then we can compute a corresponding expression like this. The goal of the receiver filtering is to make sure that the scalar value here for user I should be similar to the signal QI transmitted by user I. If we collect all of these receiver filters for the K users as the columns of a matrix capital A, then all of the processed received signals can be written like this. Y multiplied with A Hermitian. And then A Hermitian gets multiplied with the first term and with the second term. And then the goal of the selection of this entire receiver matrix is to make sure that after we have processed Y like this, it should become approximately equal to the vector with transmitted signals, where approximation could mean anything here, in some good sense. When we considered receiver processing previously, we found out that the optimal receiver processing in terms of maximizing our capacity lower bound is called MMSE receiver processing. And there were a particular geometric interpretation of it. Every user have a channel estimate that is pointing in a particular direction. It's a vector. So we have one direction pointed out by the estimate of the channel to our desired user, user I. And then we have all of the other estimates from 1 to k, but excluding gi hat. Since these are m-dimensional vectors, they are spanning a k-1 dimensional subspace of the entire vector space of m dimensions. And this is what this plane here is illustrating, as if there were only 2 dimensions. But you can view this as being a k-1 dimensional hyperplane. And typically, the vector that is pointing out the channel of the desired users is pointing in a different direction. That means that in our receiver processing, there are 2 extremes that we can consider. One is to align our receiver filter with a desired signal vector, pointing in this direction. Another choice would be to select a receiver filter that is orthogonal to the subspace spanned by all of the co-user channels. And the optimal MMSE receiver is doing something in between these 2 different extremes. So it finds the optimal balance between getting a strong signal with MR and getting rid of interference with selecting something that's orthogonal to the subspace. And this is something called zero forcing that we will consider later in this lecture. And mathematically, MMSE processing can be written as taking the estimate of the channel vector to the desired user and multiply with the inverse of a matrix that is containing a sum of the estimates of all of the other users' channels, written here as an outer product. And we have the transmit powers. Here we have the summation over the estimation errors for all the users. And here we have the noise covariance matrix. And this matrix, when taking the inverse here, will identify the optimal trade-off between getting a strong signal and getting a little interference, determined by these different terms. One thing that we should remember when it comes to receiver filters is that the scaling doesn't matter for these vectors, because we are scaling the desired signal, the interference, and the noise by the same amount. So for Emma, we can multiply with any scalar number here in front, and it won't make a difference. And the same thing applies for MMSE receivers. This BI matrix is specific for user I, but I will now show you that we can actually rewrite it so that it doesn't become like that. Using the following matrix algebra result, if you have a vector A and multiply with an inverse of a matrix B, then we can add A times A Hermitian into that inverse. And that will not change the direction of this vector, only the scaling. And here is the scaling factor that needs to be applied. This means that we can add the outer product between the channel estimate and itself, multiply with the square of this power into this inverse. And the only price to pay is that we need to multiply with the scalar number in front of here. So there will be a different constant in front. But as I said, we can put any constant here. So when we are utilizing the second expressions in the rest of this lecture, I will actually use the same scalar as before. What the goal of this lecture will be is to look at what happens with MMSE processing asymptotically. And with asymptotically, I mean when we have many antennas, or when we have a high signal-to-noise ratio. What happens with MMSE processing? Will it be close to the maximum ratio processing? Will it be close to zero forcing? Or will it be close to something else? To facilitate that asymptotic analysis, we start with reformulating the MMSE processing once more. I will use the capital G hat notation for a channel matrix containing all of the estimates as columns. And remember, d eta here is a diagonal matrix containing all of the power control coefficients. Then this is the MMSE receiver filter for one user after applying the trick that I presented on the previous slide by adding the missing term into this summation, so we are summing over all of the users, not excluding user I. And the interesting thing now is that we can utilize this notation in order to write this summation as follows. So I take all of the MMSE receiver filters, I put them into the columns of the matrix capital A. I write it like this, and I first notice that the expression inside of the matrix here doesn't depend on I, it will be the same. And this expression here can be written as taking capital G hat, multiplied with the power control matrix, and then take capital G hat Hermitian, and multiply the whole thing with row uplink. This will turn into this summation over here. I keep these two terms being the same, and then for the different receiver filters, I should multiply with different channel estimates from the right. And what I do then is that I just place the capital G hat matrix from here. And I have the different power control coefficients multiplied here with the square root of them. So I take this matrix and I take the square root of it and multiply from the right hand side as well. Now every column in this capital A matrix is equal to the corresponding expression from up here. Next, I will rewrite the expression using the following matrix algebra result. If you have a matrix B, you multiply it with the inverse of a matrix containing B times D plus an identity matrix. And the important thing is that B and D can be multiplied like this, and they can also be multiplied in the opposite order. So these can be matrices with the same dimensions, both of them being square matrices, or being rectangular matrices that allows us to be able to multiply like this. Then the interesting thing is that I can switch the order on B and D and write dB if I move B to the left hand side, and this might potentially change the dimension of the identity matrix if these two matrices are not squares. To apply this matrix identity to this expression, I'm first noting that my B will be this capital G hat multiplied with the power control matrix, and D will be its Hermitian transpose. So that will give us this expression here when I multiply B with D. And here I have an identity matrix, there is a scaling factor in front, but that can also be put into this type of matrix identity, it will still work. So then I move the B matrix to the left hand side, I change the order of B and D, get this expression, and here I'm only changing the dimension of the identity matrix from M to K, because now I have an inverse of a K by K matrix instead. And I'm rewriting the expression like this in order to permit some asymptotic analysis later, where the second terms here with the identity matrix will go away. And then it's important to remember that typically M is greater than K in a massive MIMO system. So that means that the channel matrix, when we take the outer product like this, is going to be having rank that is k. And here we'll also have a rank that is k, but in this case the dimension of the matrix is also k by k. So a term like this will actually be invertible, while this matrix is not invertible. Let's now use this second expression in the rest of this video and consider the asymptotics. And we start with the case when we have a high signal to noise ratio, and we are assuming that m is greater than k. Here is the expression for the MMSE processing from the previous slide. And if we have a high SNR, that means that the row uplink terms will be large. When we have high SNR, it is the row uplink term that becomes large. And it appears in all the terms in this expression except this noise covariance matrix. And the SNR also affects our estimation quality. So if we are looking here at the variance of the channel estimates, and we let row uplink go to infinity, well then this term and this term is large, the one here can be neglected, and everything cancels out here except beta k. So what that essentially means is that the estimation error variance, beta k minus gamma k, becomes 0, because gamma k turns into beta k. We have such a high SNR that our estimates become perfect. So our capital G hat matrix here is turning into the true channel matrix. We are now ready to see what happens with the MMSE processing matrix when we have high SNR. So to allow us to take the limit, I start by taking the MMSE processing matrix and multiply with the square root of row uplink. Remember that we can scale our receiver filters in any way we like. Then I divide all the terms by row uplink. So then row uplink only appears in the noise covariance matrix here as 1 over row uplink. Then if I let row uplink go to infinity, 3 different things happens. The noise term goes away, gamma k goes to beta k, so this term goes away, and finally g hat goes to g. So what remains is the g matrices, and then we have d eta number of times. If I pull out things from the inverse here, this is the final expression. G multiply with an inverse of g Hermitian g, and then we have only one d eta with an inverse square root on it on the right hand side, because this term here will cancel out that term and this term will be moved out to the right hand side of the matrix inverse. If I now consider a large but finite value of the SNR row uplink, I can say that my A matrix will be equal to this expression divided by the square root of row uplink. I apply this to my received signal vector y, and that means that I should multiply A Hermitian with the signal term, this term, and with the noise term, like this. And the square root of row uplink is appearing here, and it disappears from the first term. The interesting thing is that we have the channel matrix G here, and then we multiply it with the Hermitian transpose of this term. And that gives us a expression with G Hermitian G multiplied with G Hermitian G inverse. So these terms are cancelling out each other. This is a pseudo inverse to G Hermitian. Furthermore, the d eta and d eta with an inverse here, both of them have square roots, they are cancelling out each other. And the only thing that remains in the first term is the transmitted signal vector Q. So my received signal will contain Q, and then a processed noise term that is normalized with SNR. And as the SNR goes to infinity, also the SNR disappears. So at high SNR, what we are getting is precisely what I called zero forcing earlier, a method that is cancelling out all interference by creating a pseudo inverse to the channel matrix, and then at high SNR eventually also the noise is disappearing. Let me explain the geometry of maximum ratio processing and zero forcing. So say that we have a desired signal that comes in with the channel vector, the blue one here. Then we have one interfering signal that is having this channel vector, and then there is noise, and the noise will be spread over all directions. Here I have drawn this in 2 dimensions, which means that we essentially have 2 antennas, but it generalizes to more dimensions as well. And what we do with our receiver filtering is to pick one out of these 2 dimensions. And remember, when we have 2 dimensions, we can rotate our coordinate system in any way we like. And what maximum ratio processing is doing is to focus on the direction of the desired signal. So we apply a receiver filter based on that one, and that means that we will get some of the interference left. Namely that we are projecting the vector representing the interfering channel onto our desired signal vector, like this. So we will get all of the signal power and some piece of the interference, because this interference vector is having a shorter length than the original one, but there will still be some part of interference left. This is what maximum ratio processing is doing. If we do zero forcing instead, then we would look for another direction, namely something that is orthogonal towards the interference vector. Here we have such a dimension, and if we are now projecting our desired signal vector onto this dimension, we get something that is substantially smaller. However, if we are projecting interference onto this dimension, we'd get nothing. So we remove all interference, but we only get part of our desired signal power. And at high signal-to-noise ratio, when we don't need to care about the noise, it's only the interference that is limiting us, then we would like to get rid of as much interference as possible. What about the case when we have many antennas? Well, once again, here is an expression that we will have for MMSE processing. I will not provide an exact asymptotic analysis this time, but only noticing the following. That we have G hat Hermitian, G hat, and the diagonal elements of this matrix contains the squared norms of the different users' channel estimates. And the more antennas we have, the more terms we are summing up here. We know that the average is proportional to m, and therefore we can say that also for random realizations here, we will have values that is growing with the number of antennas m. The other part of the inverse is a diagonal matrix, scale identity, containing different terms that is independent of the number of antennas. So if we have a large number of antennas, then the contribution of these terms to the diagonal of the entire matrix here will be smaller and smaller in relative terms, and therefore eventually we can neglect this term altogether. So when we have many antennas, we throw away this term here. What remains is this term here. And if we rearrange in a similar way as before, we pull out the rho uplink, we pull out the d eta terms, then we can rewrite it in this form here, which looks very similar to the zero forcing expression that we had earlier. The only difference is actually that we are having the estimates of the channels here instead of the exact ones, because now we are considering having many antennas, which is providing us with sort of a high effective signal-to-noise ratio when we are transmitting. We are getting strong signal due to the beamforming during transmission, but we will still have a limited signal-to-noise ratio during the channel estimation, so the G hat here will still be imperfect. So the message here is that when we have many antennas, the optimal receive combining turns into zero forcing, but based on the estimated channel matrices. So when we previously considered a massive MIMO regime with many antennas to motivate the use of maximum ratio processing, the point was not that it would be the optimal method. Maximum ratio processing is essentially never the optimal method when you have multiple users, but it's just that it worked particularly well in that case. But zero forcing is the optimal method in at least the single cell case here. So therefore we would like to obtain a capacity lower bound when using zero forcing for any number of antennas. The only important thing that we should remember is that this inverse matrix here, which is a k by k matrix, where we are multiplying an m and k matrix with each other like this, only exists when we have more antennas than we have users. So we need m to be greater than k. Since products of Gaussian matrices are appearing like this, let us consider them in more detail before moving on. If Z is an m cross k matrix with IID complex Gaussian random variables with variance 1, and m is greater than k, then if we take Z and multiply with Z Hermitian, we get what is known as a complex Wishart distribution, and we also say that this is a complex Wishart matrix. Wishart matrices of this kind is showing up all the time when analyzing the performance with zero forcing. So let's look at some of its basic properties. This is going to be a k by k matrix, and if you compute its expected value, we get m times the identity matrix of size k, which is showing us that if we are taking one column in Z and multiply with the corresponding row in Z, we are getting the square norm of one of the columns, and that one have an average value equal to m. And if we take different columns and rows here, then we are getting something that is independent of each other. They have zero mean, and we get 0. What is less obvious is that if we are taking a complex Wishart matrix and we are taking its inverse and compute the expected value, we still get something that is a scale identity. But now the scaling in front is 1 divided by m minus k. And this is one of the expressions that we will utilize when analyzing zero forcing. And remember, this was the expression I had for zero forcing, but we can also utilize that G hat can be written as a matrix of this kind with ID elements if we are just multiplying with a diagonal matrix containing the gamma values and then the square root of them, so the variance of the corresponding estimates here. If we rewrite the expression using this, we can write the whole thing as set times set Hermitian set inverse, and then we will get this matrix showing up here. And finally, remember that any scaling can be applied to a combining matrix like this, and actually we can apply different scaling to different columns because those are the different receiver filters. So we can take away these two diagonal matrices, and we can also take away the scaling factor and say that when we're analyzing the performance with zero forcing, we can just as well write the matrix A like this: set times set Hermitian set with an inverse on it. Let's now consider what happens with the received signal Y when we are using zero forcing processing based on the estimated channels. And remember that the exact channel matrix, G, is equal to the estimate, which can be written like this, minus the estimation error that we can gather in the matrix like this. So if this is our original received signal, and we replace G with this expression, we get one part here containing the channel estimate, written like this, and we have one additional term here that we subtract containing the estimation errors. And then we apply our zero forcing matrix A, written as on the previous slide using the set matrices. We take the Hermitian transpose of it and multiply from the left hand side. We are then getting set Hermitian set inverse like this. We get set Hermitian like this. And then we should multiply it with this term. We have a set. We have the two D matrices here containing the gammas and the etas. And then we have the transmitted signal vector Q. And we take the same expression and multiply it with this term containing the noise and the estimation errors. And as expected for zero forcing, this term here becomes an identity matrix because this is a pseudo-inverse to set Hermitian. So here in front of the desired signal, we only have an identity matrix multiplied with two diagonal matrices, and then we have the transmitted signal vector. If we now zoom in on the ith element of this vector, the one that should contain the data symbol for user I, this is what we are getting. We have square root of row uplink. Here we have a 1. Here we have the square root of gamma I. From here we get the square root of eta I. And here we have the data signal qi of this user. And that is the only term from this sum that is showing up because of this identity matrix. And then we take the ith element of this vector as well. And we can now notice that here we have the desired signal multiplied with some kind of deterministic channel, multiplied also with some transmit powers. And the rest of the expression, we can call it W, and we can say that this is uncorrelated interference and noise. And these properties can be utilized in order to use capacity lower bounds that are applying when we have a deterministic channel and uncorrelated interference and noise. And in order to use such bounds, we also need to know what is the variance of this entire term. And we can notice that these two different terms here are independent of each other because the set matrices are containing the estimates of the channels, and W is independent noise, and here we have the estimation errors which are independent of the estimates. If we look at them separately and compute the covariance matrix for this term, like this, we see that we get set Hermitian set inverse multiplied with set Hermitian set, and then we have set Hermitian set inverse again. So two of these terms are cancelling out each other. We get only the expected value of a complex Wishart matrix, and remember it is equal to an identity matrix of size k multiplied with 1 divided by m minus k. And for this part here, this is the covariance matrix of the noise, which is an identity matrix of size k, and the covariance matrix of this term will give us an identity matrix of size k, and then this term that you might recognize from the MMSE expression, because it is the estimation error variance for each of the users and the transmit powers of the corresponding users that we're adding up. And since these are independent random variables, we will get the constants here as the variance of the W variable. So we can compute a capacity lower bound using the capacity bound for deterministic channels. When we are transmitting a signal X, which in our case is Qi, We are scaling it with a transmit power, rho, which in our case is rho uplink times eta I. We have a deterministic and known channel coefficient g, which in our case is square root of gamma I. We are adding w, which is all the other terms. And then we are receiving something that we are decoding, and we have this capacity lower bound, where we should take rho, multiply with the absolute value square of this term, and divide it with the variance of the remaining term. And in our case, rho is rho uplink times eta I, and g is square root of gamma I, so we square it and get this expression. And the variance of w was the product of the two constants that we had in the covariance matrices on the previous slide. If we compute the ratio between the two different terms, we can move the m minus k into the numerator, and then we get this capacity lower bound, which to a large extent looks similar to the capacity lower bounds that we have seen previously. But now it is for zero forcing, and we are essentially using what we call a use and then forget technique, because we are knowing the set matrices, but we are still, when we are computing the variance of the effective noise W, assuming that we don't know set anymore. This capacity lower bound has the typical form log 2 of 1 plus a signal to interference and noise ratio. There is no small scale fading visible here because we already averaged over the randomness. In the numerator, we have three different types of terms. We have a coherent beamforming gain, which grows with number of antennas as m minus k. And an expression like this is only making sense when m is greater than k. So what we see is that we have m antennas, but in order to cancel out interference, we are sacrificing some of the antennas. This doesn't mean that we are getting rid of some of the physical antennas, but with our m antennas we have m dimensions that we are observing, and we are throwing away some of them because the interference is there, and what is left is m minus k. And the bottom line is that we are sacrificing some of our dimensions in order to get rid of interference. Then we have rho uplink times eta I, which is the transmitted power. We have gamma I, which is the estimation quality. In the denominator, we have the noise term here, and then we have a sum over all of the users, including the user I, which is the user that we are considering here. For each user, we have rho uplink times eta k, this is the transmit power of user k, and that is multiplied not with the variance of the channel, but the variance of the estimation error of this channel, which is beta k minus gamma k. This happens because we have taken the true channel, divided it up into the estimate that we know, and the estimation error. And for the estimate, we have taken away the interference using zero forcing. But for the estimation error, we don't know it, so we still have some uncertainty there. We cannot get rid of any interference. So we are effectively getting interference here as if the true variance of the channel was equal to the estimation error variance. So we get less interference, but the price to pay is this reduction in beamforming gain from m, which is what we're having with maximum ratio, to m minus k, which is what we are getting with zero forcing. So if we are comparing the expression with maximum ratio and zero forcing side by side, everything looks the same except that where we with maximum ratio had an m, which was our beamforming gain, with zero forcing we get m minus k because we are losing some dimensions when we are cancelling out the interference. However, the benefit comes in the interference term, where we had beta k originally, the true variance of the channel, and now we have beta k minus gamma k, which is only the variance of the estimation error. If we are comparing these two different methods in the simulation scenario with 10 users, beta is 1, we have pilots at of length k, and we are letting all our users transmit with full power. If rho uplink is minus 5 decibels, we get this graph here, where we are varying the number of antennas at the base station, and we are computing the rate that each user is getting in bits per second hertz. And note that all the users have equally good channels, so this is for an arbitrary user. I have curves with maximum ratio processing, with zero forcing processing, and also with the optimal MMSE processing that we have considered previously. What we can notice is that maximum ratio and MMSE processing are equal when we only have one antenna, but otherwise there is a big gap between MMSE processing and MR, and that is something that we have noticed previously as well. When it comes to zero forcing, we need to have at least 11 antennas before m minus k becomes a positive number. And that also means that when we have too few antennas, then zero forcing doesn't work particularly well. And notice that we are actually operating at lowest null already. But when we are adding more and more antennas, zero forcing beats maximum ratio processing and it becomes closer to MMSE, but there's still some gap here. If we increase the SNR to plus 5 decibels, which is still a fairly low SNR, we see that MR and MMSE processing give us the same result when we have only one antenna, but then as the number of antennas is increasing, we get a big gap. When it comes to zero forcing, we see that it still needs 11 antennas before it becomes functional, but then it increases rather rapidly, and after just 20-25 antennas here, we have something that is a very close approximation of MMSE processing. So this is in line with what we have seen before. At high SNR or with many antennas, we have that zero forcing is close to MMSE processing. And since the equivalence between MMSE processing and zero forcing was appearing asymptotically, if we both have many antennas and a high SNR, the gap will be particularly small. We have only talked about the uplink so far in this lecture, but we can also define a zero forcing precoding. So if the uplink expression is that the matrix A is like this, set times set Hermitian, set with an inverse, then this is how we are distinguishing between the different user signals in the uplink. We are processing our received signal to listen to the orange user by taking away all interference from all the other k-1 users. When designing precoding, we can remember the principle from before that we should transmit in the directions where you heard the users most clearly in the uplink. And that means that we can apply the zero forcing principle both to separate the users when we have received signals and to transmit signals to the users in a way where we are causing no or very limited interference between them by tuning the beams so that we are not transmitting directly towards them, but in such a way that the leakage between the users becomes very small. The downlink zero forcing precoding expression is obtained by taking the expression that we have in the uplink, take the conjugate of it, because the channel matrix is G in one direction and G transpose in the other direction. And then we need to normalize the matrix, so while it's in the uplink, doesn't matter what scaling the different columns of A have. In the downlink, it is important because the norm of every column is determining what power we are assigning to the particular user. And we have been utilizing the idea that every column should have a squared norm, which is on the average equal to 1. And this scaling factor can be identified by utilizing that A Hermitian A have an expected value that we obtain using Wishart in matrices like this. So it's the same m minus k that we have seen previously. We can compute a zero forcing expression in downlink as well. It looks like this. And if we compare the uplink expression and the downlink expression, we can see many of the similarities. They have the same structure. The beamforming gain is m minus k both in the uplink and in the downlink. And the rest of the numerator is also the same, except for that we have row uplink here, and here we have row downlink, because this is the maximum uplink power, this is the maximum downlink power. Here we have eta I, gamma I. It's the same expressions that we are getting in the uplink and in the downlink when it comes to the numerator. The denominators also look fairly similar, but we should remember the difference between interference in the uplink and interference in the downlink. In the uplink, the interference comes from the users. They are the ones transmitting. So the interference that have to do with the signal from user K is actually transmitted over the channel from user K, and that is why we get beta K minus gamma K showing up here, the estimation error variance for user K. While in the downlink, all of the signals that is reaching user I comes from the same channel from the base station. So that's why we have beta I minus gamma I for all of the signals, even if they are meant for different users. Then we have the same noise variances in both cases. In this lecture, we have talked about 3 different processing methods, and which one should we utilize? Well, let's compare the 3 different options. We have MMSE processing, which is providing us with the highest performance, but it has a rather complicated capacity expression that we have talked about in the previous lecture. It contains an expectation in front of a logarithm, and that is an expectation with respect to the small scale fading. So it takes more effort to compute it. Then we have zero forcing processing, where we have a closed form expression. We require m to be greater than k in order for this expression to make sense. MMSE processing can be used together with any number of antennas. But it has the same complexity to compute as MMSE processing. It's essentially the same kind of thing. You have an inverse of a matrix multiplied with the channel to the user. It has inferior performance, but when we have high SNR or many antennas, or preferably both, then the performance of zero forcing is close to that of MMSE processing. So one can view zero forcing as a lower bound on the MMSE processing's performance. And finally, we have MR processing, where we also have a closed form expression, and in many cases it has greatly inferior performance. However, it also has the lowest computation complexity because there is no matrix inverses. And in the beginning of the development of Massive MIMO technology, there were a lot of interest in maximum ratio processing because it was believed that the complexity of zero forcing and MMSE processing would be too high. And it might indeed be like that when you have very many antennas. But for 100 antennas or so, we can definitely apply zero forcing and MMSE processing because actually the complexity of the inverses is mainly dependent on the number of users, K. So I would say that the main choice is to use MMSE processing. It has the highest performance, but if you would like to predict its performance analytically, we can utilize the zero forcing closed form expressions. And if you would like to have a baseline performance lower bound, then maximum ratio processing is the method to utilize, just to figure out that if we are building the system, we should at least get this performance, but hopefully we can get the performance predicted by zero forcing and achieved using MMSE processing. This video has been about zero forcing processing, which is a method we can use in the uplink or in the downlink of a multi-antenna system to cancel interference between the different users. And the optimal MMSE processing is turning into zero forcing when we have many antennas or a high signal-to-noise ratio. And a good thing with zero forcing is that we can compute capacitor lower bounds, both in uplink and downlink, in closed form. And this expression is telling us that we can get rid of most of the interference, but not the things that are unknown to us, namely that the remaining interference is proportional to our estimation error variance. And the price to pay is that we need to sacrifice the number of antenna dimensions equal to the number of users.